Welcome to the afternoon session of today's talk. So the first talk is by Jens Marklof, who will speak on geodesic random line processes and the roots of quadratic congruences.
Great, thank you very much. So I will talk to you about a new application of homogeneous dynamics to number theory. And it's of course a great honor and a great pleasure to talk in front of such distinguished audience, in particular Professor Dani, who has made so many seminal contributions to the field. And I've counted my papers that rely on Dani Margulis estimates and also, of course, Dani correspondence. And it's quite a few of them. So I'm not sure I would be standing here without you. So thank you very much and happy birthday. So this is a problem, an old problem in number theory, concerned with the roots of a quadratic congruence. So a quadratic congruence is simply an equation in integers where you look at the solutions mu squared congruent to d, where d is a fixed positive integer, take it to be square free. And you take that mod m, where again m is fixed in the congruence. And now we would like to understand the asymptotic distribution of such roots. And asymptotic here is relative to the parameter m. So m goes to infinity, d is fixed. For each m, we get a collection of roots, a finite number of roots, mod m. And what we'll do is we want to understand the distribution in the unit interval. So we have to normalize our mu's by m. So they become numbers mod 1. And you ask now the first question is, are they uniformly distributed mod 1, right? One of the favorite challenges in number theory. And the answer is yes. What is important here, I just want to highlight this, is that we don't just look at the mu over m here for fixed m. We order the full sequence for all m up to some capital M. So we order them by them. We order them by increasing denominator. So we truncated some capital M, if you like. But I'd rather like to think of this as an infinite sequence ordered in this way. And so now we have uniform distribution. So this is our infinite sequence. And that was proved by Christopher Hooley in 1963. He was, in fact, in Cardiff for a long time. And in the last few years of his life, he lived in Bristol and he gave a few beautiful lectures in number theory there. Now, so that's uniform distribution. And then, of course, there was a whole industry. First of all, Hooley himself extended this to higher order polynomial congruences. Then the question around for error terms was studied by Bykowski using modular forms. A harder problem is when you don't go through the full sequence of m, but you restrict to primes. That's very famous work by Duke, Friedlander, and Iwaniec, who showed that if you restrict the m's to primes, you still get uniform distribution. Zahavi, who is from Tel Aviv, student there of Zeev Rudnick, looked at joint distributions, and also Kowalski and Sundararajan showed recently that this kind of uniform distribution results are actually a consequence of a much more general framework around the Chinese remainder theorem. Yeah? Say again? You said something about ordering. Yeah, so you just order by increasing m, okay? So you write down, first of all, the mu over 2, mu over 3, mu over 4. For each m, you get finitely many numbers, and you just order them in this way. That's it. Okay, and yeah, it doesn't really matter in between. So if you have a term with the same denominator, you don't need to order them because they're only finitely many. So they don't actually change the result. Right. Okay. So What I'm really interested in is to go beyond uniform distribution and ask the question, how random is a sequence actually that's uniformly distributed mod 1, right? Because of course you have sequences that are uniformly distributed mod 1, but they're not random at all. They don't look random at all. To actually quantify good statistical tests that bring out the randomness in the distribution is something I find fascinating. So there are two statistics here that I want to discuss with you. First of all, the first is the gap distribution. So we have this infinite ordered sequence. We just look at the first n terms, mod 1 ordered, that's important. And then we look at the gaps between them. So of consecutive terms. And let's label them as S1 up to Sn. No, so these are just ordered in the way I've described. Now I take mod 1, then they're not necessarily ordered. So I need to now look at consecutive terms. So if you want to relabel them, you have to reorder them, right? To make sure that you really get consecutive gaps. So I don't want to just write down psi j plus 1 minus psi j because they might have other terms in between. Yeah, is that clear? So we just look really at the gaps between consecutive terms. And I label these gaps as S1, Sn. We have exactly n because we are taking things mod 1. Redefine the gaps. I can define the gaps. So I have points here. And let's think of this as the interval modulo 1, so 0 and 1 are identified. And these will be my xi1 up to xin, not necessarily xi1, xi2, but they could appear in any form, right? So then I call this difference here between the first two consecutive S1, this one here is S2, and so on. And the last one here is Sn. They're good? Right. So that's the so-called gap distribution. An easier statistics to handle analytically, precisely because you don't need to order things, is the pair correlation function. That's a second order statistics. And here you simply take the differences between all the gaps that correspond to non-identical elements. So I'm excluding m equal n here because it would just give trivially 0. And this sum over L here, integers, is just ensuring the mod 1 condition. And you've seen in both cases, I'm blowing up the whole distribution or the gaps and the spacings by n. And the reason for this is that the average spacing is 1 over n, right? You have n points on the unit interval, so the average spacing is 1 over n. If you wouldn't rescale, you wouldn't see anything in the limit, anything non-trivial. So you need to blow it up by n. And so you can think of here this as a probability distribution that you test against bounded continuous functions that has sort of a mass at all the gaps. And here you can think of this as a density that has a mass on all those spacings. And now you ask yourself, well, does this have a limit? And we say that, yes, it does if it converges in a weak sense. So these probability measures Pn and this density Rn converges weakly in this sense to a limit. And the observation is that if your xi j are uniformly distributed random variables that are independent, then almost surely you can show that the limit, you can't show almost surely, you can show that almost surely you have convergence. It would be great to prove theorems almost surely, no? Huh? Yeah, well, with respect to what measure, right? That's the question. Okay, and so in the first case, the gap distribution has a limiting probability density e to the minus s. That's exactly the waiting times for a Poisson point process. So in some sense, it's what you expect for a random sequence. And the 2-point function has a constant limit density. There is a 1 here in here, yeah? And that's what you see. Okay. So I would, in these cases, say the gap and 2-point statistics are Poisson. for the reason that these are exactly the answers you get for a Poisson point process. Now, the exciting thing is that these are not the only answers you can see for very natural point processes. There is the so-called random matrix distribution, or random matrix distributions. There are many there. And for example, if you take a random matrix in the space of n by n unitary matrices, you can pick one at random with respect to the Haar probability measure on this space. You can diagonalize your unitary matrix. You get n points on the unit circle. That's our unit circle, right? So these would be the eigenphases of your eigenvalues. And then you can show that almost surely there's also a limit, so-called Godin distribution, which is a very, it's a sort of functions you can't write down explicitly. You can find an approximation that was found by Wigner that looks like that. So it's a curve that I'll show you on the next slide. And however, the 2-point function has an explicit limit density, and that looks like this. And the exciting thing about this, it actually appears for some very fundamental sequences. For example, the imaginary parts of the Riemann zeros on the critical line. So when you do this, now I might be confusing you a little bit because I've just talked about just points on the circle, but you can do the same for points just on the real line, right? You have a sequence on the real line. You can look at the gap distribution and the 2-point function. And if you do this, and you compare here, this is the Godin distribution. It's like the actual approximation to the Godin distribution. So it's not the s squared t to the minus s squared term that I've showed you on the previous slide, the Wigner semis. Kotlitska actually used the actual data here, the actual approximation. And here you see a histogram that is coming from the actual Riemann zeros in a very, very high interval up on the critical line, 10 to the 12 of size 10 to the 5. And it is a conjecture, an open conjecture, that actually the Riemann zero statistics converge to random matrix theory. This is completely out of reach at the moment. Montgomery did some beautiful work here where he proved a very weak form of this conjecture, which was later extended to also 3-point and n-point statistics. This paper by Rudnick and Czarnak is an absolutely beautiful paper where they actually explain it really nicely. Let me put it this way. So if you look at Montgomery's paper, he doesn't even use test functions. He just uses one test function, and the whole thing looks very complicated. Once you understand that you're really looking at densities here, tested against test function, the whole picture becomes much clearer. And that's what Rudnick and Czarnak did. And we're able to extend Montgomery's limited range regime to all endpoint correlation functions. Yeah, sure. Yeah. That's good. So why don't we think about that a little bit? So when you have a probability distribution, you just need bounded continuous, right? That's the weak convergence. And why is that? Well, because it's a probability distribution, so you actually don't need compact support. The 2-point density was not a probability density, so it's just a density. Exactly, it's just a point density. So that's why you need the weak star topology or the vague topology in the language of point processes, right? So you need to actually truncate it. You could, of course, be more ambitious and say, oh, I have a function that decays at infinity. That would be a stronger statement, but it sometimes actually goes wrong because you have mass accumulating at infinity, right? So that's why. So that's the distinction. One case probability measures, and the other it's locally finite. Yeah? Okay, good. I'm glad I could answer the first question. Now, let's go to number theory. And here we have some really surprisingly simple sequences for which it's extremely hard to prove convergence of those statistics. So if you take a polynomial mod 1 and I'm just focusing here on n to the power d alpha mod 1, where alpha is some irrational coefficient. One can show, and that's a very beautiful result, just using quite elementary number theory techniques, that for almost every alpha, the 2-point function converges to the Poisson answer, so a constant density. We don't know what's happening for the gap distribution. There's again, a very beautiful paper by Rudnick, Sarnak, and Zaharesco in Invenciones, where they show convergence along subsequences to the correct answer. Unfortunately, that's for well-approximable alpha, whereas if you don't expect convergence along the full sequence for well-approximable alpha, we expect Diophantine conditions so badly approximable, for instance, or at least not well-approximable, anything with a Diophantine type kappa less than 3 should work, according to their conjecture. So no proofs, even for the 2-point function for a specific alpha. So this problem has a bit the flavor of a quantitative version of the Oppenheim conjecture, where you look at quadratic forms, and if you look at indefinite forms, that is actually a 2-point statistics. And that's how Eske, Margulis, and Moses got into this game. So this has very much the flavor, but we're not there yet. So we can't prove what we can prove for quantitative Oppenheim, where you have a form and you have some Diophantine condition and you can prove that it converges to the uniform density. Here we can't do it. We don't know if for alpha equals square root 2 and d equal to 2, so n squared alpha mod 1, this converges to the expected limit. Right, so that was the preamble. And now I'm going to turn to this work that is with Matthew Welch, who's now in Maryland. And here we look, if you remember, at the roots of the quadratic congruences. And you've already seen that, there are more interesting distributions than just the Poissonian. There's the random matrix ensemble. And you also maybe appreciated that it's already not trivial to prove convergence at all. So the fact that these things converge to a unique limit is a very, very non-trivial statement. So in this theorem, we prove that if D is not congruent to 1 mod 4, there is a continuous limiting density, WD, so that the 2-point function of our roots converge to a limit, WD. It's a continuous function, and you see it here. It's the black curve. And what you see in the background is a numerical experiment that we've done for the first 10 to the 6 values in our sequence psi j, and in the case when d is equal to 2. Here's another numerical experiment for d equal to 3. So all these all satisfy our congruence assumption. And here it is for d equal to 10. So you see the curves change, the distributions are different, and they certainly don't look very universal, right? So what is behind this? That's what I'm trying to explain to you in this talk. How we prove it, what's behind it, and yeah, how does homogeneous dynamics come into this picture? Now, before I do this, I just want to explain that actually we can prove the convergence of all statistics, all local statistics, not just the 2-point function. So we can prove it for the gap distribution that I showed you, the next to nearest gap distribution, and all other statistics that fall into this realm of measuring correlations between points on the scale of the mean level spacing. So to formulate that, we use the language of point processes. So you define a counting measure on R by just putting a delta mass and at every point of your sequence. And it is something that lives on the unit circle. So that's why we have the sum over k here. That's just the mod 1 again. You could say it lives on the real line, and then I just periodize it. Yeah. So and then we shift by psi. And psi, you think of a random variable that's distributed to some Borel probability measure. Just think of the uniform Lebesgue measure in 0, 1. That would be already sufficient here. So you basically throw down your sequence. So this sequence here, if you like. Yeah, the first n, then you make it periodic to get something that's on R, and then you just throw it down at random. And that's a point process. That's a random point process. And now you say, well, what's the probability of finding k points of this random point process in a fixed interval? And because I want to fix the interval, I have to do the same thing again. I have to blow up my sequence to make the mean spacing 1, right? So then I get a point process of intensity 1. And now I just ask, well, will this point process converge to a limiting point process? And our theorem will say, yes, it does. So that's the meta theorem, if you like. As I said, this implies convergence of joint gap distribution. We can prove convergence of all moments. And actually, the 2-point density is a special case. It's a special second moment of these distributions. Okay. We can also impose further congruence conditions on NM mu, which leads to different limiting processes. You'll appreciate that once I show you how we prove this. Okay. So the key is to understand how we can translate the problem into a problem of hyperbolic geometry. And then we're going to apply, as we've seen in this conference already, uniform distribution of horocycles. That'll be in the background. Okay, so H denotes the upper half plane. Boundary is DH. SL2R acts by Möbius transformations. I don't need to explain to you how geodesics and horocycles look like, but there are a few examples here of geodesics in this picture, and no horocycles. I'll denote the stabilizer of a point or a geodesic stabilizer group in this way. So C could be a curve here, or a horocycle, or a geodesic. It could also be a point. Gamma infinity is the stabilizer at infinity. So that's just this group. Viewed as a subgroup of SL2Z. H mod SL2Z is the modular surface. SL2R modular SL2Z we view as the unit tangent bundle of the modular surface. C will be a closed geodesic or a horocycle. And it will be closed if the intersection of the stabilizer with SL2Z is a non-trivial subgroup of SL2Z. And an important object in this game will be Z sub C, which is going to be the top of a geodesic C. So I'm only thinking of these kind of geodesics here. So here I have a geodesic. The point CZ will be this. I'm not considering here vertical geodesics, even though formally you could say, well, it's the point at infinity, but we're not gonna do that. An important remark that I want to make is that in general, when you take a geodesic, you look at its top, so over here, and then you compare it with the top of the image of that geodesic that will in generally not be the image of the top of the first geodesic. Yeah, it will have moved. Is that clear to everyone what I'm saying here? No? Good. Okay, thank you. So let me make a picture. So I have here my geodesic C. I have a top. Now I've carefully moved all the colored chalk over here when I started preparing. And then we have here CZ, okay? And now you map this, the new geodesic. And this is silly, of course. Let me do this as an example. So, of course, if I just go to C plus 1, then the top will not have changed, because the top will just be CZ plus 1, yeah? But if I do a different non-trivial operation, what will happen if I map this geodesic over here, then this point will have moved here. So this will be gamma z sub c, whereas this will be the point gamma c sub z gamma sub c, yeah? So you can do this as an exercise and check if I'm correct. I always tell my students, I'm not always right. And so, gamma is on the left. I'm acting by Möbius transformations. Did I write it on the left, on the right? No, no. Gamma acts on the left. Okay, brilliant. So now we have a theorem here that relates the roots of the quadratic congruences to tops of geodesics. So the theorem says that for D as above, there exists a finite set of geodesics C1 up to CH, so that for any M, that's our mu mod M, right? That's our quadratic congruence. D is fixed here. D is fixed. There exists a gamma, okay, so that we have this relation. So we have a gamma so that we map our original geodesic from this finite set. Just think of one geodesic here. That applies in many cases when you have sort of narrow class number 1 for your number. Then we can write that top geodesic as mu m plus I squared d over m. And the mod 1, remember this is all mod 1 here, is translated now mod gamma infinity, because just this gives us the shifts by 1, right? So that's an actual thing. And to get some uniqueness here, we therefore mod out on the left by gamma infinity, because if we replace this gamma by some left translation, we still get the same identity here, nothing changes. And from the right, we need to mod out by the stabilizer of this geodesic. As it turns out, these geodesics that I've written down here, they actually project to closed geodesics on H mod SL2Z. Yeah, so they're closed ones. So their stabilizer is non-trivial. If I replace gamma by gamma times an element from the stabilizer, I still get the same result. So it's natural to look at this double process. And that makes it sort of 1-to-1. So we also have the other direction here. And as I said, this extends to more complicated congruence conditions and so on. You can, in fact, have a similar parametrization of roots in terms of SLNZ relations. So the degree corresponds to the n in SLNZ. The degree of the polynomial. So you now will not look at mu squared, but you have another polynomial, mu cubed, mu to the power 4, or something more complicated. And that's in a beautiful paper by Matthew Welsh that was just published this year. And that was essentially his thesis. So have a look at that. That's more of a number theoretic results. Of course, we're dreaming about doing something similar here for SLN, but we don't quite have, even though we have this correspondence, we don't quite have the homogeneous space interpretation, the dynamical interpretation to extend this. To answer questions about those fine scale statistics. And also recently, the theorems that I showed you have been extended to D congruent to 1 mod 4 by my student Zonglin Lee and Matthew. Okay, so let me now explain to you how this roughly works. And this all goes back, if you like, to Gauss, who understood that there is a relation between quadratic forms and SL2 R, in particular when you have indefinite quadratic forms with integer coefficients, you get this beautiful relationship between the sort of symmetric matrix that defines the form and the action of SL2Z that acts here by this sort of conjugation, if you like. Transpose gamma acts on the matrix, or transpose gamma times matrix times gamma. And so you can then define equivalence classes of forms with the discriminant D as the orbits of this action. The solutions of this quadratic equation define the endpoints of the geodesic. And I think you've also all seen this, that the closed geodesics on H modulo SL2Z are exactly characterized by the endpoints being roots of a quadratic polynomial. And then you have the correspondence with periodic continued fractions and the geodesic flow and the closed orbits of this. So I hope you all remember this or have seen this before. I'm not going to use it in this talk. I'm just throwing you some little pieces here so that you can see the connection with some other very fundamental, beautiful mathematics. So the quadratic forms correspond to geodesics in H 1-to-1 that are closed in H mod SL2Z, and the equivalence classes of those geodesics correspond 1-to-1 to the closed geodesics of the same length LD in H modulo SL2Z. Now, the connection between what we're doing in terms of the, yeah? Huh? The second line of, yeah. Yeah. Yes. So that means that all... No, from the same equivalence class. Yeah, yeah. So they're not the same geodesic on the surface. They're various, but all the same length come from the same equivalence class. Yeah, so this is, I mean, what I recommend is read Peter Sarnak's thesis, and he has a beautiful paper on exactly working out the, the average over the HD, so counting geodesics in the congruence class. So it's, I don't want to spend time explaining it here, but what I want to explain is just the connection with our quadratic congruence. So if you look at our quadratic form up there, and you choose D to be equal to 4D, as I say it there, and you take A to be M, B to be 2 mu, what you see then is that f x1 equal to 1 leads to the equation 4D, and maybe I shouldn't write it so close to here. So that leads then 4D to be equal to 4 mu squared minus 4 mc. And you see, if you take this then modulo m, you get, so you divide by 4, obviously, then you get mu squared equals d modulo m, right? Because the c here gives you the mod m condition. So that's the simple relation between the quadratic forms. And maybe I should also just explain to you, give you an example. For instance, when D is 2, let's say, so this is the fundamental domain of the modular surface. And let me just show you what the geodesic corresponds to in the case D equal to 2. So I think I've already made this too large. So this is point I here. And for D equal to 2, we basically go, this is 1, minus 1. So we need to go roughly to, or precisely to minus square root 2 and square root 2. Square root 2 is 1.4 something, right? Yeah, so I got that roughly right. And now let's draw the geodesic over here. And the point is now that if you look at the orbit of this geodesic under gamma, you get a whole collection. And inside the fundamental domain, what you'll find is that you get parts of, you don't know really where this is going to end up here, but this is just a translate of this other geodesic. So here, this is actually a closed geodesic, because what's happening? Let's start here. We have periodicity. We're mapped over here. We move there. We're coming back here, and we move down. This is an inflection point, and we move back, right? So do you see this? We move along this geodesic. Is actually closed geodesic in the modular surface. And that's the example in our theorem that would correspond to the congruence mu squared is 2 mod m. And in this case, we would only have one geodesic in that theorem that I showed you. I need the slides back, please. Do I need to do it? What do I need to do? I need to share the screen. How do I share the screen? The green thing, yeah. Okay, which screen am I sharing? Yeah, don't worry, I've done this before, not just on this machine. Share. Oh, great, look at that. So this is the picture, and just to show you, now this thing needs to wake up. That. Okay, I'm stuck. I shared too much, I think. Thank you. Right, so we were here, and what I've just showed you was the version of this theorem, and where is this gone now? My theorem's gone. Here, the version of this theorem when D is equal to 2. In this case, we just have one geodesic. This would be C1, yeah? And inside, the projection of it into the modular surface would be this triangle. And that would be the geodesic that plays the main part in this story. Okay. So now I hope I've illustrated there's a connection between the roots of the quadratic congruences and geodesics, yeah? The geodesics have a top, and the top of this geodesic corresponds to the quadratic congruence. So the way you need to think about this, you need to now start with this yellow geodesic and look at the orbit under gamma of this geodesic. And you get many, many tops all over in the hyperbolic plane. And each top corresponds to a solution of my quadratic congruence with a fixed d equal to 2 for this one. So that's the first chapter, yeah? So you need to accept that now. No more arguing. Okay, so that's the first message. Good. And now I need to explain to you how we can now understand the statistical properties of the roots in terms of the statistical properties of the tops of the geodesics. And in order to do that, I'm just going to forget about our application. And I'm just saying, I'm looking now at any hyperbolic surface with a cusp at infinity, let's say that. And I'm looking at, what did I just say? I'm looking at any hyperbolic surface with a cusp at infinity. I pick one closed geodesic, your favorite one, or also a finite collection of them if you want. And then I look at the orbit of this closed geodesic lifted to the upper half plane under the group gamma. I get a whole lattice of geodesics. Do you all see that picture? I mean, it's a bit like this. That's basically starting with this geodesic, and then I look at all the geodesics that I can obtain by acting with my discrete group. So here it is. That's the kind of object I'm looking at, and I want to understand their distribution. Okay, and how do I understand the distribution of an object like that? Well, I'm just going to look at their tops, because that's what I'm interested in anyway. The tops of those geodesics, and I'm actually interested, as you know, in my quadratic congruence. So I'm just interested in the real parts of those tops, right? So just remember our theorem was the real parts where the root appears. And I think of this here as some kind of truncation. So because our sequence is ordered by denominator, this gives me a nice way of truncating the sequence. Okay, so that's what I'm doing. Forget about the number theory application. Just think about the top of the geodesic. I want to understand the distribution of the real parts ordered by the imaginary parts, yeah? So I'm looking at all tops with the imaginary part bigger than y, and I'm taking the mod 1, and I'm interested in the statistics of this set. What I want to show, it's again a finite set on the unit circle. As y goes to 0, I get more and more points. And I'm just asking exactly the same question. Is it uniformly distributed? What are the gap distribution? What are the pair correlation functions, etc.? Yeah? Okay, so that's exactly what I'm going to do. So I'm going to count now the elements of my set in the unit circle, and I'm asking how many points fall into a small interval of size y, shifted by x modulo 1. You can see the green dot. The green dot is quite important here when I say something. So watch the green dot. Okay, so that's what I'm counting. And the reason why I normalize by y is because I know that there'll be roughly y points in this xy. Yeah, so that's the right normalization. Remember, I'm looking at fine scale statistics. So I want to have, look at correlations on the scale of the mean separation between points. And that's going to be y here. So I need to rescale everything by y. Does that make sense? Before I was blowing up the sequence, now I do the opposite. I'm scaling the interval down. It's the same thing. So let's define this strip in the upper half plane. starting at height 1. So it's exactly this kind of strip here. This would be the strip if I is the interval -1, 1. That would be an example, but remember I scale it down now. So I scale my interval I down. I can take any interval I want here. It doesn't really matter, just a nice interval. And now I want to understand exactly how many real parts of my sequence fall into the small intervals and that have height larger than y. And I can rewrite it in terms of this strip, right, in this way. So these are the elements of our sequence. I do the cosets to get uniqueness here, not overcount. And so the strip makes sure that in this scaling that because I'm multiplying by y, that my imaginary part is bigger than y, and my real part is in this interval also scaled by y, right? That's the beauty of it. You just multiply by y and it does it all for you. Good scaling. Okay, that's the first observation. So this is the most important part, by the way, of this lecture. And then you realize that you can absorb the mod z condition by removing the coset. Does everyone see this? So here I was doing things mod 1. So I would overcount if I wouldn't have the coset. I would get infinitely many points, right? Because I'm doing it in mod 1. But now I'm just undoing my periodicity of my strip. I just look the actual strip because it's inside the fundamental domain of the z action. I just get 1 point, even without doing the gamma infinity here. Or yeah, so I now overcount if my y would be fixed and I would be too big, I would overcount, but I'm choosing y sufficiently small so that it fits into the fundamental domain. So this is correct. And then here's the beautiful thing. You just suddenly realize that the multiplication by y and the translation by x is, of course, realized by Möbius transformations. These are Möbius transformations corresponding to those matrices here. Good. And that's where we have our action of SL2R. X is going to be random because I'm going to throw down this interval at random. So we're going to average over X, and therefore we're going to average over a horocycle. And that's where our horocycle average will come in. Y is going to go to 0. That's just the geodesic flow. So what do we have here? We have a translate of a horocycle. Brilliant. Okay. And you all know that translates of horocycles become uniformly distributed. Yeah, again, your old work on invariant measures for horocycles with Smiley, but of course, in particular, showing that closed horocycles become uniformly distributed is something we're going to use here. But now I want to understand the limits for the distribution of my point set. Yeah, so I have these tops of my geodesics. And I'm sort of counting how many fall into this strip. And now I want to explain to you how we can characterize the distribution that we find in terms of a limiting random point process, because that was in our theorem 2. And so this is also, I think, something that hasn't really been discussed in the literature. So I'm thinking here of geodesic line processes. Each top uniquely parameterizes a geodesic in the hyperbolic plane. So I can think, when I think of a random point z, I can also think of the random geodesic that's attached to it. And now I'm going to just set up a random line process in the hyperbolic plane. So if you have never heard about random line processes, you might have heard of point processes, yeah? So a random line process is exactly what a point process is, except you don't throw down points at random, you throw down lines at random. Now, secretly, every line process is also a point process because you can parameterize lines in Euclidean geometry, hyperbolic geometry by points, of course, right? However, it's a nice geometric interpretation to think about random lines. And here, as I explained, the points are parametrized by the top. But let's just think of random point sets. So, okay, for a test set B, let's define the number NB of a top point here and its images, that's what we're looking at. And now I'm translating by a general S element in SL2R. So that's my G, and I'm putting the inverse here for a reason that'll become clear later. So if I do this for a general G, then you realize that if I put G equal to NXAY, I get exactly the quantity I was interested in, yeah? Everyone happy with that? So all I've done here is I've extended my definition on the previous slide to more general matrices G. I note that this counting function is independent of replacing G by gamma G. So it lives on G mod gamma from the left. Okay, and so with this count, this motivates now for me the definition of a random line process. As defined here. So that's the actual original thing we're interested in for our points. Remember, this was the X, and now I think of X is a random variable Xi, which is the random translation. And here I have another point process, parametrizing my line process, where G is now distributed according to Haar probability measure on G mod gamma on the left. Yeah, so we're now playing on this space. No, yes. Now, you can define an intensity measure. So the intensity measure of the point process is simply the measure that you get when you take the expectation of your point process evaluated against a test set B. So that defines a Borel measure. And what we see here is that this intensity measure, so one needs to prove this. So this is like a Siegel type formula here that I'm showing you, that it's just the volume measure on the hyperbolic plane. Yeah, okay, let's go on. And now what we can prove is that the number of tops of geodesics that fall into this little interval here, probability for random X, that there is exactly K points, converges to the probability that my random point process intersects in this strip here, this blue strip, in exactly K points. And we don't need to do, it just works not just for one interval I, but for a whole collection of intervals. So if you want to test independence between different intervals, then that's what you do, right? So you ask, what's the probability that there are K1 points in this interval, K2 points in that interval, and so forth. So we can prove this. And that actually completely characterizes the convergence for the point process, or in this case, the line process, if you think of it as random lines. And you see here the analogy with the equidistribution of closed horocycles, where we average a test function over a horocycle and translate it by AY. And our well-known result is that this converges to Haar probability measure on G mod gamma, SL2R mod gamma. And you see the correspondence here. We also average over X, and we have a limit, which is the same object just averaged with respect to Haar measure. Of course, you need to do something to go from here to there, which is looking at or respecting the fact that F here is a discontinuous function, but as long as the discontinuities are measure zero with respect to the limiting measure, you win. And this, in a sense, is a complementary result to what people had studied before when you were looking at analogous problems of orbits of points under a discrete group gamma, where you can also look at these directional statistics. So this was work started by Boca, Pasol, Popasarescu, Kerman Kontorovich, Riesager, Serdegren, who used analytic methods to study this. In my paper with Ilya Vinogradov, we developed this kind of approach to show that actually you have a really nice geometric interpretation of this directional statistics. And this is an extension now from points to lines. But of course, the main thing is the application now to our number theoretic problem. Just to say, we can also do the same thing for moments. We need to look at unbounded test function, and that can sometimes be very subtle, as we know from the proofs of the quantitative Oppenheim conjecture. In this case here, we can deal with any moment, even though our test functions also diverge, but they diverge not so fast that we can't deal with it. Okay, our theorem also implies uniform distribution of those tops of geodesics. So in particular, Hurley's result just follows from our approach almost immediately. You don't even need to look at it. Yeah. Okay, and I'm going to leave this out. What you would have seen here is that in order to get to statistics like the gap distribution, you could just take our theorem on the convergence of point processes, and there is a statistical argument that shows you that once you know that, you also know the gap distribution. But there is a very nice way of seeing the gap distribution directly, something that was pointed out in a beautiful paper by Threya and Chung, where they looked at gaps between Fari fractions. And the same thing works here. So they designed a surface of section for the horocycle flow, and the return times were exactly the gaps of the Fari fractions. Now here, the same thing applies. So we can find a section which is different from the Threya-Chung section, which gives us the gap distribution of the roots of the quadratic congruences at the return times to the section. And I've written down what the section is here. If you want to know more, you can ask me in the Q&A, okay? Because I don't want to go over time. I'm probably already over time. And we can prove a nice equidistribution theorem with respect to the section using standard techniques, going from the flow to the return map, standard techniques from the surface of section method. I think that's something that appeared in Uri Shapira's talk as well. That kind of going from the flow to the section. We looked at the different objects. Okay, I'm going to skip this slide about palm distributed point processes. Just to say, here is the formula for our pair correlation density. I'm just going to flash this. So we can actually work out something explicit. Yeah, you can write down the formula. However, it's still not super explicit in terms of elementary functions, as you see. It still involves a sum over double cosets. Now, not double cosets with respect to gamma geodesic modulo gamma infinity. It's now double coset with respect to two geodesics. That's coming out of the calculation. And this is the formula. I'm not going to go through it. So just to remind you, these are the curves that we get if we put that formula onto the computer, and we just, all we need to do is we sum over these double cosets, evaluate the functions, and then you get those curves. So that's why they look very non-generic, because they are non-generic. Okay, those densities. But it's quite amazing to see this very precise agreement with the numerical data. So happy birthday again. I hope you like this, because you've been working also on closed geodesics and so on. The main difference here is that we actually just fix the geodesic. Normally we'd like to count all closed geodesics up to a certain length and things like this. Here, the limiting object is just coming from one geodesic or multiple ones, and then you sort of randomize the picture. And that gives you a limiting process that explains this very number theoretic object. So I think that's kind of a cute application of hyperbolic geometry and homogeneous dynamics. That as far as we are aware, haven't been found yet. I mean, people use automorphic forms, but it's a different type of hyperbolic geometry that is used there. I mean, it's not that this is just an interpretation of it. It's sort of orthogonal to it, I would say. Good, thank you very much.
Any questions or comments?
I don't think, oh, okay. I have two questions. First is, what happens as this number D goes to infinity to the distribution?
Beautiful question.
Thank you.
So that's the question I get asked in every talk, and that's the question also we ask ourselves. And that's certainly on my list of to-do things. What I would expect is that as D goes to infinity, and certainly if we now move through the Ds for which you have sort of generic closed geodesics, I would expect that these statistics become Poissonian. And the nicest thing is to think about the surface of section. So the surface of section, thank you for asking about that, is the following. You start with your closed geodesic. So I'm now doing a sort of just a topological picture here because, so you start with a closed geodesic. That's the object C that we have. Actually, let me go back to the formula for it. And you see exactly what I mean. Here it was. This is the section, the SL there. So you start with a C, what's called C head L here. That's our geodesics. Then you turn by 90 degrees. We are in phase space, right? So turning by 90 degrees means the geodesic vector is pointing in this direction. Now I'm turning. Each point. Actually, we are in a three-dimensional space, so I should draw it like that. So these are now orthogonal. Yeah, so we've turned. And then we flow with the other geodesic action. No, not with the other, with the same geodesic action, but now with respect to this new tangent vector. So we now flow orthogonal to the original geodesic with a geodesic flow. So we get something that'll look like this. And yeah, I'm intentionally drawing it as going closer and closer because you can show that in the metric, that's what's happening. So you now have these images here. Yeah, and so it goes something, it looks something like that. It's actually coming close together. And in fact, if you would go to infinity, it would be finite volume. So we start here with our original and then we flow this way. So that's the section. Yeah. We have to truncate it at some point in the proof where we show that the truncation doesn't matter. And then you see if that initial geodesic, the blue one, is actually wild in the surface and you think of the return time to that section, you could sort of imagine that it's pretty Poissonian. But that's just a conjecture. It would be nice to prove that. We might have to average over D to prove something like that. As I said, if you just give me a bit more time, and I have a sabbatical next year, then that would be a great problem.
Any other questions? So I had a quick question. So this is not Poissonian.
No. It's not Poissonian, you see already, because the pair correlation function is not flat, right? It has this thing. It's becoming flat as you move to infinity, and that's something also we can show, but it's not flat.
So no more questions, and let's thank Jens again.
Thank you.